Hello everyone. We are from Group B and we are representing Bcss. Today, our team is proud to present our research proposal titled Fingerprint-Based Authentication System for Secure Student Portal Access. Accompanying me today are my group members. If you guys can introduce yourself, please.
My name is Muhammad Himan Aidil bin Muhaidi.
My name is Raish Nusai bin Razman Akili.
My name is Tuan Hazek Kimi bin Tomadu Isham.
Okay, thank you. So now, let's begin with our next slide. To give you a roadmap of our 20-minute session today, we will start by discussing the strategic background and contextual parameters driving the study. Next, we will break down our two primary problem statements. Next, we will then articulate our core research aim, the three measurable milestones we have set, and our scope boundaries. Following that, we will explore our systematic literature review metrics. And then finally, we will walk you through our technical methodology, displaying our system architecture schema, our conditional process flowchart, and our project timeline milestone. So let us look at the foundational reality of our campus environment. Modern university student portals are high-value target hubs packed with confidential personal information. We are managing official transcripts, payments, profile, residential logs, and enrollment records. Unfortunately, institutional access security historically prioritizes convenience over defensive hardening. Legacy portals remain completely anchored to simple alphanumeric password strings matched against a public student ID. The operational risk here is tied directly to human cognitive friction. Managing dozens of unique passwords is mathematically annoying for an average user. Consequently, students routinely choose predictable phrases or systematically recycle the exact same credential combinations for their central academic profiles as they do for secondary public platforms. Public forums or gaming networks. According to Verizon's 2023 Data Breach Investigation Report, compromised credentials are the direct catalyst for over 80% of all recorded enterprise breaches. When a minor third-party platform leaks data, automated threat actors buy those logs and execute massive automated credential stuffing attacks against university infrastructure. Localized mobile biometrics present an alternate architectural gateway to block this remote vector entirely. Right? This brings us directly to our core problem statement. Our first problem statement focuses on the fundamental flaw of text-based validation. Exclusive reliance on static text strings means that an academic profile can be breached instantly without threat actors ever needing to target central university mainframes directly. They exploit human recycling habits. This structural exposure cannot be mitigated by simply telling users to pick a stronger character or using arbitrary password policies. Our second problem statement highlights that severe user friction caused by legacy multi-factor authentication patches, specifically network-reliant SMS OTPs, and the dense concrete architecture of our university facilities, most notably the upper vertical layout of the Unicap MIT Tower block, create structural cellular dead zones during high-stress critical operational windows like module registration week, delivery pipelines, for text messages regularly stall or fail entirely. Waiting minutes for a code while limited class seats fill up creates extreme frustration, leading students to actively avoid the portal. Security controls should not degrade core usability. I will now pass the floor to my colleague to define our research framework target.
Alright, thank you. Now we are going to talk about research aims. Okay. To successfully address the vulnerabilities outlined by my peer, our team has established a precise research aim, which is to design, develop, and validate a functional cross-platform mobile applications prototype that removes static password fields entirely, replacing them with localized device-level fingerprint verification tailored into student workflows. To realize this primary aim, our framework is bound by three highly measurable technical research objectives. Our first objective is to run a target systemic review of current database credential vulnerabilities to categorize the precise attack classes successfully blocked by biometric controls. Our second objective is to engineer a functional cross-platform mobile prototype utilizing native iOS and Android cryptographic biometric API frameworks integrated directly with the token-backed microservice configurations. And our third objective is to empirically test and analyze the application defensive boundaries against physical spoofing or digital replay loops while tracking the actual user acceptance pattern via a targeted undergraduate field trial. Next. Next is our scope and significance of study. To ensure complete development feasibility within our single semester time, but we have locked down clear execution boundaries. Our target cohort is limited to currently enrolled undergraduate students in the UniKL network utilizing their personal smartphones. The software environments are restricted to native code builds optimized for Android API 28 and above, and iOS 15 and above. We leverage native hardware keystore extensions. For our functional scope, we are strictly programming with the token lifestyle, cryptographic validation loops, and identify handshake. External portal features like reading database or scheduled reads remain out of scope. Finally, the biometric modality is locked strictly to single source fingerprints, excluding facial measures or iris scanning to retain development focus. The significance of this title is twofold. Practically, it offers an empirical blueprint for modernizing administrative security, providing our campus IT engineers with a clear reference architecture to patch credential exploits. Academically, it bridges our prominent literature gap. Local Malaysian biometric research stays heavily focused on corporate physical attendance log or office tracking, completely neglecting higher education portal access security. I will now hand over our next presenter to walk through our systematic literature metrics.
Okay, thank you. To ground our prototype in established scientific boundaries, we executed a comprehensive literature review. As you can see in our report, our analysis cover 17 distinct empirical sources. For the purpose of this presentation, we have isolated our core thematic anchors. So for the first one, looking at Abdullah and Ali 2021, their case study provides empirical backing for our first problem statement. Tracking that automated credential stuffing drives a staggering 85% of unauthorized university portal entry attempts. Second, the comparative study by Patel et al. 2021 proves that moving to biometric touch steps reduces entry delay by 60% while simultaneously documenting that over 65% of students admit to recycling password strings across low security platforms and critical student profiles. Furthermore, Okutpuji et al. 2020 executed one of the few direct field integrations in an active university setup, confirming that an empirical 78% drop in unauthorized access attempts post biometric deployment. To validate our safety architecture, Zhang and Liu 2023 performed a security analysis on mobile APIs, verifying that platform native layers like Android's biometric prompt guarantee biometric hashes stay locked inside local hardware execution environments. and are never transmitted over the web. Finally, the survey by Kasim and Othman 2022 confirms our second problem statement, which shows that Malaysian student finds SMS OTPs highly disruptive due to cellular signal propagation limits inside deep concrete university blocks. Okay, next slide. Okay, continuing our synthesis matrix on our next slide, we focus heavily on defense mechanism against threat vectors. Kumar and Singh 2022 highlight that physical spoofing using artificial modes remains the primary threat to mobile sensors, demonstrating that integrating software-based liveness detection cuts spoofing success rates by roughly 40%. This directly informs our prototype's architecture. On the technical side, Lee and Kim 2021 analyze hardware-backed key stores, validating that cryptographic token signing within modern smartphone chips prevents token extraction even if the host operation system kernel is completely compromised. Culturally, Muhammad and Zainal 2023 show that giving users complete structural transparency about where their biometric data is processed elevates user adoption metrics by 40%. This underpins our onboarding interface layout. Ultimately, the collective literature validates that our proposed prototype balances user speed with enterprise security. I will now pass the floor to our final... Oh, my bad. Okay, next slide. Okay. Okay, for the technical methodology, architecture, and roadmaps, let's elevate how our team plans to bring this system to life. For our system development cycle, we have explicitly chosen the Agile Scrum framework. When engineering mobile applications layer linked to native security APIs, developers routinely encounter integration bugs, minor hardware variations, or deprecation blocks. A rigid waterfall layout would slow down fixes by breaking our 12-week timeline into discrete, iterative 2 weeks functional sprints. We can construct core modules, deploy local testing scripts, and adjust backlog dynamically. Furthermore, as for undergraduates with completely different class timetables and varying coding proficiencies, Scrum's adaptive rhythm allows us to distribute tasks fairly without any single roadblock stalling the entire project lifecycle. Our data collection and empirical testing products operates across 2 independent tracks. Track 1 leverages an attitudinal survey utilizing a 5-point Likert scale instrument distributed via student networks to gather entry data from 50 unique MIT undergraduate trial participants. Track 2 is our empirical hardware lab, where we will deploy our code onto several test smartphones to actively measure performance latency, calculate error states, and monitor how our liveness detection modules react when exposed to high-resolution printed spoof images. Now I will hand to the next presenter.
Okay, thank you, Hilman. So this slide displays the native schematic of our proposed system architecture block diagram, which separates operations into 4 distinct vertical pillars. The data flow is entirely decoupled. When a student initializes the app, it does not send credentials over the network. Instead, the mobile client interacts natively with the local device hardware sensor. Once the chip reads the fingerprint, the phone's internal isolated co-processor, which is the trusted execution environment on Android or the secure enclave on iOS, uses a unique private key generated during user enrollment to mathematically sign an authentication payload. This signed cryptographic package travels securely via HTTPS and TLS 1.3 to our cloud API gateway. Our backend authentication microservice processes the package, validates the digital signature against the user's stored public key matrix, and if verified, issues a signed JSON web token, the short is JWT, session wrapper back to the client. As explicitly marked in red, raw biometric signatures never leave the personal phone boundary, nullifying centralized data theft risk. The next slide. So to complement our structural architecture, this slide outlines the conditional logic map of our operational process flowchart, mapping out our system guardrails from start to end. The app initializes and captures the dermal layer, It instantly hits our first major diamond decision gate. Is liveness valid? If our software scripts detect a spoof, a synthetic mold, or printed image, the runtime routine halts immediately and displays an authentication failure error. If liveness passes, the isolated secure chip signs the token payload using the private key, passing it over an encrypted channel to our cloud gateway. The microservice runs its asymmetric signature evaluation. If the digital signature matches, the backend validates. If the digital signature matches, the backend validates the handshake, generates a secure JWT, and grants the student active access to the portal hub. If the signature validation fails at any point, the request is rejected and logged. Next slide. So this slide shows our exact 12-week development roadmap, structured to match our Gantt chart table milestones. We dedicate week 1 and 2 to phase 1, which is focusing on backlog crystallization, requirement specs, and survey distribution. Weeks 3 and 4 cover phase 2, where we map database entity relationship models and build high fidelity interface wireframes. For week 5 and 6, it introduces our missing text link, phase 3, or development sprint 1, where we construct the cross-platform UI blocks and bind the native Android and iOS biometric APIs. For week 7 and week 4, we focus on phase 4, or development sprint 2. We compile our backend token services and hook up our liveness detection modules. For week 9 and 10, we focus on phase 5, running our physical spoofing attack vector labs and compiling latency metrics. Finally, week 11 and 12, we close up phase 6, where we refactor repositories, finish our final dissertation thesis compilation, and submit our project deliverables. Next slide. So in conclusion, by week 12, our team will deliver 3 core research outputs. First, a working software prototype, displaying clean native biometric bindings. Second, an empirical analysis log charting our security resilience thresholds against proof vectors and processing delays. Third, complete process maps matching user acceptance metric summaries from our field deployment. Believe that by replacing outdated passwords with privacy first, hardware backend biometrics, we can create a convenient, secure environment for our university student portal. Thank you for your time. Thank you. That's all from